qubit that is more stable than some of what the other competitors are using. So I'm going to go ahead and just kind of jump right in here and just kind of talk about some of these concepts.
Hey, Rick,
yep.
one quick thing. I can't start recording. Can you see if you can?
I sure will.
It keeps telling me there's an error, so I'm wondering if our outage is...
It says it's recording.
Okay.
So it looks like you're rolling, baby.
Okay, go ahead, man.
Yeah, okay, awesome. So yeah, as I was saying, there's been some advancements. A lot of people don't quite know or aren't aware that Microsoft has been working quite a bit in the quantum space. We are working on a particular type of qubit, as I mentioned, that is a little bit more stable. It's got some different properties and some different challenges and some different benefits than some of the other technologies, but we are convinced that this particular type of qubit is going to be, we think at least, is going to be a bit of a winner chicken dinner. So the real question, of course, is, and it may be obvious to some and it may be completely oblivious to others, but what really is quantum computing, right? So when we talk about subatomic particles or atomic particles, they can be atoms, ions, photons, electrons, right? There's different ways of approaching this problem. And ultimately, what we're trying to do is we're trying to get away from a 0/1 type of approach, right? So if you think, I'll get to in a second, but the nice thing about quantum computing is the concept of a qubit or the atomic particles can actually represent multiple states, which is actually really cool. And there's some other theoretical stuff that we'll get into. I shouldn't say it's theoretical. It's actually been proven in some cases of some of the concepts within the space of quantum computing. So as I mentioned, atomic and subatomic particles effectively are replacing our classical transistors, the 0/1 type of capability. There's three big kind of concepts. Well, there's lots of big concepts in quantum computing, but there's really kind of three, I would say three that kind of rise to the top. And one of them is probabilistic computation. One is superposition, and then of course quantum entanglement, which are all derived from the laws of quantum mechanics, right? So if you've ever watched Big Bang Theory, right, you've heard people talk, they were always talking about string theory, and they were, talking about quantum entanglement and some of these concepts. So they are legitimate computer concepts that they were actually talking about, or quantum mechanics concepts that they were talking about on the show, believe it or not. And we've actually been able to quasi-solve and address some of them today. So that last bullet is kind of interesting, is that they can solve problems that are not addressable today. So what that means is with classical computing, there are certain things simply it's just too difficult. There's too many permutations. There's too many, steps. There's too much memory that's required. There's too much compute required. Regardless of the situation, there's just a lot of different problems that this type of computing can actually address, right? So the nice thing about this is that this can open up a whole new realm of doing things like modeling, weather predicting, right? Where I don't know about anybody else, but I kind of stopped listening to the weather person quite a long time ago, simply because the challenges that exist in the forecasting and the modeling and some of these other technologies that are used today just don't quite seem to be able to cut it anymore. Security is another big space within the realm of quantum computing. I'll show you a slide in a little bit, but suffice to say, with this additional compute power brings some interesting challenges and opportunities around security. So I'll get into, so we talked about those three kind of main components, or the higher level components, right? And the first one is really superposition. So if you think about a classic bit in binary or within a transistor, as we talked about, right, you basically have zeros and ones, right? On, off, 0, 1, true, false, yes, no, that kind of thing. With quantum particles, you basically have a certain probability of being 0 and a certain probability of being a 1 due to a phenomenon known as superposition. In quantum mechanics, this is also a concept that's also called coherence. Okay, so a particle, basically, if you're using an electron or whatever it is, it has its own 0 or 1 properties, and we refer to that as spin. Okay, so while we say it can be 0 and 1, it does have a 0 and a 1 property. And when we talk about spin, basically we're talking about the orientation. Okay, so is it up, down? Think of it like a compass, right? A compass will always point north, but you can orient that compass in different ways, and that's considered the spin. Okay. So when we talk about classical computing, we'll just say 1 or 0. I'll just kind of keep things easy and keep it kind of simple, right? So when a quantum particle is in a superposition state, it is a linear combination of an infinite number of states between 0 and 1. And if you look at the image that I've got on the screen, you can see that Qubits got those dots in there. And so think of it as like not just a 0 and a 1, but almost like an XYZ coordinate, right? Because we want to actually measure it. Okay, so here's the interesting thing about a qubit. You don't know which, so I talked about the probability of being a 1 and the equal probability of being a 0 in a previous slide. You don't know which one it's going to be until you actually look at it, which is really kind of crazy, right? So you have no idea until you basically take a peek at it, which is a concept called quantum measurement. Okay, so that's a technique by which as soon as you measure it, you actually get basically effectively a return value, if you will, of what the actual value is. So when a quantum particle is actually observed or measured, it'll basically show you a 0 or a 1, but nothing in between, okay? And this is because the act of observing or measuring a quantum particle, it collapses the superposition state, right? So when I was talking about the superposition state before, I was referring it to as almost like an X, Y, and Z state. Okay, so there was like 3 kind of metrics that I was talking about. When you collapse it, think about taking a balloon or take a ball, if you will, like the old kickballs that we used to have, and letting all the air out of it and squashing it. Okay, that's called decoherence. And basically, the particle takes on a classical binary state at that point. So the cool thing about this, though, is, again, it takes on a classical binary state, but it's helpful because you can do a lot of things with ones and zeros. But once a particle has been measured and collapsed, it stays in that state forever. Okay, so imagine, if you will, when you shut off a computer, right? Your memory, your volatile memory goes away. Anything that persisted to non-volatile storage is gone. In this particular case, basically it stays in that state forever until you basically reset it. So you can absolutely reset a qubit. You can reset a qubit back to its superposition state so that it can be used for quantum calculations again. But think about the ramifications of that, right? If you have long running calculations, if you've got certain things happening where it takes a lot of compute power, you don't have to worry about thinking about mispredicting in a compute pipeline, or you don't have to worry about certain things happening that may affect that value, because that value cannot be changed until you physically reset that qubit. So it's kind of like when somebody catches you dancing and you think nobody's watching, right? And so you're getting, and somebody sees you and boom, oh, we just caught him dancing, and that's the state you're in. Okay, so that's that's an interesting way to create an interesting metaphor, but that's basically what it's like. Okay. So entanglement is the next topic. So we talked about superposition. Let's talk about quantum entanglement, right? So this is probably the most, I'll say, recognized term, because quantum entanglement is basically the ability of 2 or more quantum particles to become entangled with each other. Now, big deal, right? I can take 2 pieces of string and I can, wrap them around each other, and now they're entangled, right? But when a particle becomes entangled, it forms a single system such that the quantum state of any particle can't be described independently. Okay, so the quantum state of any of the other particles that have been entangled all represent the exact same value. Okay, they all basically are tied together, they all represent the same value, and they all correlate to the other particles as well. So in addition to this, the particles can maintain connectivity even when spread across large distances. So think about this: light years. Okay, light years away, you could have 2 particles, and once they become quantumly entangled, they basically represent each other, almost like a mirrored state for basically ever. Okay, so what's interesting about that, though, is a lot of people have speculated, and I'm not, I don't get into some of the other science around this, but there's been discussions around, people talk about doppelgangers, and people talk about, hey, that's your twin, or that's whatever, right? Well, they believe that this is a byproduct of quantum entanglement and that there are these other particles that are floating out there in the ether that absolutely are representative of each other. They're a mirror image. They maintain the exact same state at any given time. And so it's kind of crazy, right? So if one particle does collapse, right, if it's measured, then of course the other particle will collapse and as well, right? So I mentioned that in the last slide and said, like I said, they do collapse like that ball if you take the air out of it. Well, that same thing would happen to the other ones because there's a correlation between the entangled qubits. Measuring the state of one basically gives you information about the state of the other qubit. Now, the cool thing in quantum computing, if you think about that though, is if I want to farm out a workload to a bunch of, say, a high performance computing cluster, right? And I've got quantum entanglement going on with a ton of qubits that are spread across this. I don't have to report back to the mothership with a summarization. So think about like a MapReduce type of workload or Hadoop or something like that, right? I'm not necessarily feeding summarized information from a distributed, a bunch of systems crunching different disparate data. I've got all these qubits that are floating around with persisted states, right? So at any given time in a mesh type of situation of quantum computing in an HPC workload, I know the state of all the other machines. So instead of talking to the master node and communicating back, I just update basically the entangled qubit and it's reflected in the other end, right? So there's some interesting byproducts and some interesting, I think, components specifically to how this is applied, okay? The third part that I want to talk about before we get into the Azure side of the house is qubits and probability. Okay, so as I mentioned with classical computers, right, they store information in bits that are either zeros and ones, right? That's what the transistor does. And of course, we mentioned with the quantum computing, there is basically a 0 or 1 or anything in between, right? Depending on the configuration, right? So a qubit has a certain probability of collapsing to a 0 or a 1. I'm sorry, a 1 or a 0. And that qubit's probability is determined by what's called quantum interference, okay? And quantum interference can be a lot of different things. It can be temperature, right? Because one of the things I haven't talked about is the stability of qubits. They aren't very stable at high temperatures or low temperatures. They need to be really, really low temperatures for them to be stable. And so people have taken different approaches to the qubits, and they've taken different of ways of trying to solve this problem. For example, do we suspend it in a chemical compound? Do we freeze it? Do we put some kind of, is it possible that we could take, and I'm just speculating, but is it possible if we could take like a positively charged lipid like they do for transportation of like vaccines, right? Could they keep it suspended in something like that that may increase or decrease the impact of the level of the interference? So there's a couple different ways and there's a couple different approaches. And effectively, as you can see with this map, right? So if when we talk about, because of all the different values that qubits can maintain and the states they can maintain, in this slide, you can see the performance of classical versus quantum. So to represent 56 bits, okay, 4 bits per string, on the left, you see classical computing. So you see a lot of zeros and ones, right? We've got some binary and a bunch of other stuff going on there. If you look on the right, basically it takes 4 qubits to represent the 56 bits per 4 strings, right? So we can store a ton more information and we can do it a lot more effectively is the message here, right? So I'm just going to give you a few more examples, and then I'd like to jump into the Azure part, as I mentioned. So please bear with me. I will absolutely get there, I promise. Okay. So addressing classically interactable problems. So this is a real world problem. Okay. This is a really interesting piece right here. So so you see this is RSA. So it's a 2048 challenge problem. So how long would it take to basically decrypt this string, right? Because you've taken 2 different, random generated numbers and those have been used to encrypt this value. How long would it take to decrypt this string? Okay. And I'm going to ask you to come off mute and I'm going to ask for some. So in a classical computing setting, any guesses? Anybody? Literally, you can put it in the chat window. You can speak up, anything. Anybody got a guess on how long it would take to decrypt this string?
When we talking millions of years?
We are talking more than that. So this string using classical computing with traditional transistors and bits in binary, right, would take 1 billion years. Okay. Notice in quantum, it'll take 100 seconds. So think about the impact of that today with all of our SSL and TLS and we think we're all HSMs and we think we're all uber secure, and you've got homomorphic encryption and you've got elliptic curve encryption, you've got all these technologies, right? This is going to destroy that in seconds, right? So you're already hearing about, in the security space, people are coming up with quantum algorithms for security. They're algorithms, and I don't necessarily know how well they're proven or disproven given the nature of where we are in quantum computing. But again, let that sink in, right? We all feel really ridiculously secure because we're using HTTPS and we're encrypting data at rest in Azure, and we're encrypting data in transit using TLS, right? All of our data on our backplane is encrypted. Well, in 100 seconds, I can break that encryption key and effectively have access to that information. So it's scary, but it's also very promising that we're currently already trying to get ahead of the curve by developing these security algorithms for quantum. So here's the other thing. This is kind of the last thing. I know there's a lot of other stuff here, but I want to kind of get into the good stuff. So these last two slides I think are interesting. So with classical computing, basically, if you were to determine a chemical reaction, right, at a molecular level, and you want to find the ground state of the molecule as part of the reaction rate, right, the state of the energy. Classical computing, as you can see, it's an exponential problem. So the first curve says you've got X number of, say, transistors as part of the solution, right? So that's your solid line that shows kind of that curve, that hockey stick going up, right? So the dotted line, and this is an exascale supercomputer. This isn't just like run of the mill, whatever, right? So classic computer, is a solid line. The exascale supercomputer is the dotted line. So not a big increase there, right? If you look at that, you're not seeing a huge performance gain. What's interesting though with quantum computing, every time you add a qubit, you double the performance. Okay, so it's not like if you've got 2 qubits, you have to add 2 more qubits to double it. If you have 2 qubits and you add a third, you've now doubled the performance. Then you add a fourth and you now double the performance. So that's why they show this as being very linear in terms of the performance increase that you get because of how quantum computing works. And last but not least, I'm going to jump into this particular slide. So this is the Microsoft approach. So now we're talking about what we're going to expect to see in Azure. Okay, this is not something that is there today, but this is something that we've been working on. This is something that we've been developing. But this is our approach. So we're basically coming up with this universal programmable quantum computer, right? And if you look at it, though, it's interesting because it's got a series of layers, right? So at the very top, you've got the applications and the software, right? So that's effectively still looking like classic compute, right? You can run it at room temperature. Yeah, it might be nice to get it down below, whatever temperature with nitrogen, someplace in there. But for the most part, the profile doesn't look a lot different than a classic computer, right? Now, if you get into the cryogenic computer control, right? So now we're starting to get into some of the space that gets a little bit colder, right? So now we're talking cryogenics. We're talking about the temperature of deep space, which sounds no fun to me. I have one of my nightmares is actually going into outer space and dying, and so this not attractive to me at all. And then last but not least, if you can see where the quantum space is, look at the temperature. I mean, we're talking about like absolute zero, right? I mean, it is getting ridiculously cold down there in order to do this. So you can see one of the challenges, of course, is keeping temperatures down so that the quantum computers, remember, we don't, because it's that whole quantum interference piece that we talked about, right? We want to avoid that and keep the qubits nice and stable so that they can represent their values in perpetuity. So so this is just the last thing I guess I'll share. So topological are the type of qubits. So these are basically qubits that Microsoft, this is the approach we are specifically taking. So standard qubits are susceptible to the interference we talked about. Topical qubits have different properties. So they have distinct error properties. They're more robust against errors and thermal noise, if you will. They have high fidelity and they scale to large computations, right? So a lot of these things are beneficial, of course, if you want to do this at scale. But now I want to jump into some of this stuff we've been talking about, right? Let's make this real, okay? So for those of you that don't know, Microsoft has got a programming language designed specifically around quantum computing, and it's called Q Sharp. Okay, so I'm just going to share my screen here, so I may put you into screen inception for a second. Let me know when you can see my Visual Studio.
I can see it, Rick.
Awesome, rock on. Okay, so there's really kind of three demos that I've got here today. The first one is superposition, right? So if we look at superposition, basically what we're doing is we're allocating a qubit, right? So we're creating a qubit using Q sharp. So we have a use statement, which is a little bit different. Then we put the qubit into superposition. So I know this is a funky looking function call, H, right? Like seriously, that's a function call. It is. Um, but as indicated here, right, that puts that qubit in. Remember, we talked about that. You have to put it into superposition, and it now has a 50% chance of being a 0 and a 1, right? And then last but not least, we want to return reset Z, which is it's gonna measure it, and then it's gonna actually reset it, right? So effectively, what it's going to do is we're going to take that value, but then we want to flip it back, right? So if I set this to my startup project, easy, nothing. All I had to do was download the Q Sharp SDK, and this should fire off for me here. And you can see, so sampling a random number between 0 and 50, 25. Okay, so it literally, as I expressed, it literally has equal opportunity of being 0 and 1, right? So it took a set of numbers. You can see it went through all the numbers, did a random number generator, but because of the nature of the equal chance of being 0 and 1, you get a 25, right? So real super ridiculously simple example of superposition within the construct of quantum computing. Quantum entanglement, of course, as we mentioned, is the linking between these two qubits, right? So these two quantum elements, whether it's a, like I said, it could be electron, it could be ion, it could be a proton, but basically this quantum entanglement concept is effectively going to go through, and it's going to show that if I set, right, so we've got H, so I put it in the superposition, I'm going to do a C naught, because so that's going to actually put them into an entanglement state. And then what's going to happen is you're going to see, so it says count the numbers of ones we saw, and then we're going to see, and then it's going to measure how many times did we get agreement between the two values, okay? Agreement means that they were actually the same value. So you can see we tested the results, the number of zeros, the number of ones, and the number of agreements. There were 497 zeros. There were 503 ones because we toggled back and forth. And of those 1,000 numbers that we created, 1,000 times it actually represented that same value. So again, super rudimentary, ridiculously simple to set that quantum state and show that quantum entanglement's a thing, okay? But what about something more difficult? Okay, so what if we wanted to actually look at real quantum computing, right? Well, Azure gives you the ability to provision this quantum capability. So one of the things I will warn you about. So I have, what I've done is I've created a quantum workspace in Azure, okay? And this is specifically for me. It's, I don't know specifically if there's a cost incurred here. I think it is running an emulator behind the scenes, but the reason I'm cautioning people about this is if I went to provision quantum capability, there's a couple different, and this one is Azure Quantum, but if you saw, there were there was some other values that came up, right? So you see ion Q, you see 1 qubit, you see one, so there's a couple different options. Now, the reason I want you to exercise caution if you decide to do this is because they get really expensive, like ridiculously expensive, okay? So I won't provision those because I want to say there's something like 200 some thousand, give or take, like a month. So I don't suggest it. But this, so if you do a quantum workspace and it's specifically for, you can see providers. So this is the default Azure Quantum optimization. It's learn and develop. It's if I I can't remember if there's a cost, but if there is a cost, it's ridiculously cheap. But as you can see, there's other providers that you can add. So field programmable gate arrays. If you wanted to test the simulated daneling, you could use FPGAs, right? Or you could use parameter free. And so there's a lot of different options. And if you are into data science or if you're into quantum computing and some of these algorithms are going to make perfect sense to me, they look very much Greek. Okay, but you can see like a Monte Carlo simulation, right? That's a pretty standard type of, take these number of parameters and I want you to run this algorithm a couple different times with different input parameters and see what the value comes, right? So some of these may look familiar, but some of these may look very unfamiliar. Okay, so one of the concepts is I wanted to just kind of call this out is binary optimization, because you should all probably be familiar with this notion of the traveling salesman problem, right? So the traveling salesman problem is an example of this quadratic unconstrained binary optimization. Okay, I'm not going to go through all the logistics here. There's a ton of math, and as Chevy Chase would say on Saturday Night Live, I was told there'd be no math. But I will tell you that this does give you the ability to solve difficult problems like the traveling salesman problem, right? And of course, we can solve this with classical computing. But when we apply this problem to something like quantum computing, this problem gets solved ridiculously fast. Okay. So I'm going to go back and I'm just also going to show you that we do have a bunch of sample applications. Okay. So the Ising model is basically something similar to what I just showed you, but there's a whole bunch of different types. So Grover search is probably one of the most common algorithms I believe that's out there. It's a super simple algorithm. It's as you can see, it's known as amplitude amplification. And so it's again, I won't get into all the specifics on it, but the cool thing is you can do all this stuff today in Q#. Okay. And I'm also not going to get into it because partly I would get way over my head on some of these things. So I'm going to be completely transparent here. So at any rate, I definitely, if you're in the space, if this topic is interesting to you, I highly recommend taking a look at these documents. But last but not least, just in case there's any questions about whether or not we can do this in Azure. So I do have an Azure Quantum workspace that I provide. And I forget, there's a certain number of qubits that it represents. And I apologize, I can't remember off the top of my head. But it's certainly, some of them represent a considerable larger amount. And those are the ones you pay for. I think this one comes with a relatively small amount, but enough to prove a theory. So I'm going to go back to my Visual Studio. And this last example is called, I just called it Azure Quantum. And this particular project, if I can set my startup project, is actually what it's doing is it's solving a problem where I've got a bunch of, say, shipping containers, okay? And I've got to optimize by weight how many shipping containers I can place on, in this particular case, I've got 2 boats, okay? So I want to create as equal as distribution of weight between all the containers across the 2 boats as I possibly can, okay? So in this particular case, this is written in Python. So if you're a data scientist or if you're into quantum computing, this Python example might look a little bit more familiar to you. So we're importing. So the first thing I have to do is I have to basically establish my workspace. So this is the workspace that I get when I create a quantum workspace in Azure. Okay, so it provides me this information, and then it says, okay, log in. Right. So I'm going to go ahead. So I go ahead and I log into my workspace, and then in traditional Python, obviously syntax, I'm going to import list, and I'm going to import from Azure Quantum, because we do have some obviously support for Python with our quantum computing, a problem type, and a term. Right. So a term is basically going to get a list of results back. A problem, of course, is something that we're trying to solve for. And the problem type, as we'll see, where do I write down? So we've got a problem type of, it's going to use the Ising model to solve this problem. Okay. Terms are going to be my outputs. And the problem is, hey, create this big problem, which is the ship loading problem demo. We've got this problem type of Ising. And then I'm going to pass in, I want to see this list of terms come back, right? So, or I'm sorry, I want to pass in this list of terms. So you can see here, we go through a series of container weights. And then with those container weights, we create this problem. So we call this method create problem for container weights. We pass in the list of container weights, and it's saying for each one, where am I going to be placing this, right? So that's what I have to solve for. I'm going to invoke this solver, which is a parallel tempering. It's basically it's a solver that you're using to actually instantiate and solve the problem in the workspace, right? So in this workspace, you can see if it ran longer than 100 seconds, it would time out, but it does not run that slow. Now, I did have to restart all this, so I will be very curious to see if this actually runs on the first time or not. But since the demo gods seems to be sort of smiling on me, we're going to give this a shot. So this is actually an emulator that's running locally on my machine, clearly, right? It's running the Python, and it is asking me to fire up this workspace, and it's going to log in. And now we're going to start creating. So we created that, we imported our data type, strongly typed components that we want to have in there. We did define, right? So def is actually creating, it's a definition for the function. And now I've got my array of container weights. I've got my terms that I'm deriving from those container weights, right? So if we look at the terms, you can see basically container 5, and it's got different containers, and it's got the specific weights associated with it, right? So now I've got my problem. I've got my problem type defined. I've got my terms. I want to go ahead now and I want to solve this problem. So I'm going to submit. So I've got a solver now that's telling it what type of solution I want to use to solve this problem. And I'm going to optimize, right? So solver.optimize for this problem and give me the result. So this is now taking it and dumping it off into Azure, into the quantum computing emulator, and it's going to give me some results. And as I mentioned, there you go. So now we've got a printout of the summary of the results. And if we look at that, you'll see container 1, which has a weight, was placed on B. And so you can see it came really, really close, 52 to 53 tons. Didn't quite get it. And so that literally that's as close as it could get by optimizing the specific containers with specific weights to go on ship A and ship B in order to get as close as possible. Okay. So again, think about some of the different types of workloads. Like I said, you've got traveling salesman, types of capabilities. You've got Monte Carlo simulations. You've got all kinds of funky stuff that you could absolutely be thinking about as you're exercising these, right? So what I like to do, and I can't speak for anybody else on the call, obviously, but I like to learn with a purpose, right? So basically what I'll do is I'll think about, like, the traveling salesman's a great example. But let's modify the heck out of it. Okay, it's great to have 10 locations, but let's throw 100 locations at it, or 1,000 locations in it with, Latin lounge that are kind of bizarre, and let's see how it works, right? And it really gives you a feel for the type of solver that you're going to be using, right? It gives you a feel for the type of problem you're going to use to optimize, right? So it might be using typically the Ising one was the one I showed, but there's a bunch of other ones. But it's also really cool that you could, in the future, leverage things that I showed you. Like, for example, this doesn't have to be a GPU-based problem. You may want to use the field programmable gate array and offload to that stack because maybe it's got different bottlenecks or different types of constraints that those would actually be more optimal for running a workload of type quantum, right? So in a nutshell, what I would encourage people to do, if you're interested, is to go take a look at, for the first thing I would do is take a look at Q Sharp, because it effectively gives you a lot of information you need to know in order to jumpstart kind of how the language itself works, right? Because the cool thing is, at the end of the day, if you get a language that does a really good job of abstracting from the underlying technology, you really just focus on the problem, right? So I give you a lot of background on quantum computing, and we just scratch the surface. I mean, let's be completely honest, there's a whole lot more to quantum than what I've talked about. But the reality is what we're trying to do is, as a platform, is we're trying to solve that problem for you. Don't worry about the compute. Don't worry about that absolute zero layer for the quantum compute. Don't worry about the layer for the orchestrator. Don't worry about any of that stuff. Worry about solving your problems, right? Because that's what Microsoft is gotten into the business to a while back, and that's really where we want to stay. Let's get you abstracted from some of those capabilities and some of those concepts, and let's put you in the position, the driver's seat of solving the business problems. So I have said an absolute ton in the last 40, give or take, minutes. So I'm going to open it up now and take a breath and say, does anybody have any questions?
So Rick, I did pop an extra link in there for more learning opportunities going forward if anybody's interested.
Awesome. Yeah, I definitely recommend. So there is additional learning material. I mean, Microsoft is committed to quantum computing. I can absolutely tell you that, and some of the stuff that I would love to tell you about, I can't, and I'm sure Derek knows some stuff about it too. But absolutely, as soon as we can talk about it, you will definitely hear about it because this is going to be a absolute game changer, right? We're going to be looking at like crop yields, right? Is there a way that we can leverage? Can we combine best practices with organic farming with maybe some of the genetically modified farming and find a peaceful coexistence where we don't necessarily have to go one way or all the other, right? We can do stuff like how can we optimize the nutrients in the soil so that we're not constantly depleting it? Or is there an algorithm or is there something that we can do to from a carbon measurement perspective to, take on climate change? There's all these problems that we're dealing with today, but to model the problems is so ridiculously complex and frustrating. It would take all the computers in the world to stop mining Bitcoins and actually do something that, would help the planet. So, and then of course, while we're running those machines, what are we doing? We're chewing up energy, right? So, that's another yet a problem to solve. But in the meantime, we can start looking at, genetic markers and DNA sequences to take a peek at, are there certain identifiers or certain markers that are going to very predictably tell you that you may have X, Y, or Z, and we're going to proactively take care of that with a very personalized medicine because we've run a Monte Carlo simulation, X number of times, or we've done some gene sequencing, and we've determined that your best course of action is to be on this particular protocol to get healthy again. So, I think the world is our oyster, and I think there's a lot of ridiculously smart people. A lot of them probably on this call. Oh, there's a question from Aaron. What draws are there for Q sharp over Python? Oh, dude, that is a great question. Honestly, Aaron, I think a lot of it comes down to, what's your preference? If you look at Q sharp, it looks suspiciously like C sharp, right? And I think the draw there is for people that are maybe perhaps coming from a background where they have done C sharp programming or any kind of .NET programming. Absolutely, it makes it really easy. Now, if you're coming from a background where you've got Python, a lot of data scientists, a lot of people are very well versed in Python. You get to pick the language, right? That's the beauty of it is we're not trying to force you, we're not old Microsoft where you have to do VB or you have to do .NET or you have no. We want to enable this capability for everybody. So I guess, Aaron, the question I would ask back to you is what draws are there for you to use one over the other and then take that path, right? Because as you saw, they're equally supported. And in some respects, there's some actual intermingling between the two, between the base SDKs and some of the things that get pulled in. So the great question though, in terms of advantages, I don't necessarily know if there is an advantage of one over the other. Oh, financial services. Yeah, dude, that one scares me. I'll be honest. Yeah, if you think about, how many predictive financial models could you take quantum computing? Oh my gosh, that could be a case where you truly could suffer from analysis paralysis, right? Like, holy cow. But yeah, I mean, there's some amazing things. My just like everything else on the world, though, we just have to be careful that it's used for good, right? I mean, with great power comes great responsibility. Of course, if you're a spider person, I won't say Spider Man because there's some amazing spider women out there. But if you do subscribe to that theory, absolutely, with great power comes great responsibility, and the onus is on us, and the responsibility is on us to make sure that we are using this technology for, the betterment of everybody, or the making something better, and not necessarily using it for our own nefarious activities. So that's just my 2-minute soapbox on that particular topic. But I guess I'll just ask if are there any other questions? We get a quiet group today.
Yeah, basically, I think there's not going to be a sector that's not going to be impacted by
Impacted.
quantum computing. So
100%, Derek. As you're popping all these, I mean, space exploration, right? If you want to predict, what's the best telemetry, think about the Hidden Numbers movie, right? And all the math that they had to do just to bring lunar land or a lander, the landing module back into the atmosphere, right? and think about what they could have done with quantum computing. Like, like instead of that big giant, feeding the punch cards in and doing all that stuff. I mean, this truly can change. It is going to be life-changing and disruptive, right? On so many different levels. I don't even know if we can truly predict what the impact is going to be. I'm working with some customers right now on autonomous vehicles, and I can tell you it's absolutely going to transform that industry.
Well, to me, the scariest thing is, like you said at the beginning, on security, taking those 2048-bit encryption keys and just blowing them away, making them worthless.
Yep. And bye-bye. We just, in 100 seconds, cracked your code. Yeah, that's disconcerting to me too. I'll tell you the other thing that does kind of scare me a little bit is, since the dawn of the nuclear age, right? We've been told that there's no such thing as a winnable war with the weapons that we have today, right? With mutually assured destruction. Well, what if a quantum computer actually came up with a way to figure out how to win it? Those are the things that we should be cautious of, but that shouldn't stop us from advancing and keeping our eye on this technology. Because, like I said, if we use it for good, man, I think we can absolutely change the world in some pretty amazing ways.
Going back to war games.
Dude, oh my gosh. Okay, so I have to say, so I did co-author a book back in 2003, and it was about bringing VB developers into the .NET age, and that was my absolute influence. That was the thing that drew me into computers, was that exact movie. I was in third grade at the time, I think I was third or fifth grade, but almost immediately went out and actually wrote a very rudimentary game, and I called it Global Thermonuclear War. Oh, well, so if there aren't any other questions, or if you're shy, you can absolutely positively always reach me at Rick, WEY, at Microsoft.com. And as a shameless plug, I will also tell you that we do have a YouTube channel. We've taken a bit of a break this summer. One of my coworkers, Mark Garner, and I have a YouTube channel. If you search for Azure Flash News, you'll find us on Twitter. You'll find us on YouTube. But hopefully, we've got some content up there that you're interested enough in that you would do like and subscribe.
Thanks, Rick. Anybody have any last minute questions before we call the meeting to the end? Go ahead and stop the recording.
Awesome.